Hi everyone, thanks for joining me, and we're going to be talking about natural gas systems and increasing their efficiency really, hopefully quite substantially. So let me just share my screen and we can get straight on with it. And yeah, innovative technology for better efficiency in natural gas systems. And what we have really here is something that we hope will both improve safety and improve profits. And it's rare to get both of those in one hit really. My name's Paul Stockwell. I'm Managing Director with Process Vision. And if you have any comments, any feedback or questions, then please send me an email, paul.stockwell@processvision.com, or head along to processvision.com, the website, and you can pick up more information there as well. My history really is with dew point measurement and gas analysis systems throughout the years. And we've come across this issue really that the industry isn't really tackling very well right now. And if it did, then we could make an enormous step forward in efficiencies and just making things safer as well. So what we have really is an industry blind spot. We're in the oil and gas industry, and the way we separate the oil and the gas is quite critical. Yet the gas liquid separators are not monitored right now. There's nothing on the market that will permanently and effectively monitor the efficiency of a gas separator. And that leaves the operators in the dark, really. We call it a blind spot. They are in the dark. They're running their process downstream of these separators and just having to cope with liquid carryover that happens on occasions or sometimes continuously, particularly in natural gas treatment plants where it's the front end separator that should be working efficiently. So in theory, the only thing moving forward into gas treatment is gas, but unfortunately it's not, and it's a big part of the industry is having to develop systems to cope with those liquids that shouldn't actually be carried over. And foaming is a big issue with gas treatment. Depending on the severity of that foaming event, it can cost between $250,000 to $250 million, depending on the size of the plant. That's a big issue for gas treatment plants, but also in the gas networks, because carryover of liquids into gas networks is a big problem and a big no-no really. It's quite unsafe to do that, but it's happening on occasions and causing problems. So our mission, quite simply, is to stop pipeline contamination. And we have a piece of kit that we hope will help with that. So why isn't this being done at the moment? Well, there are a whole host of gas analyzers on the market doing great jobs when monitoring moisture and H2S and GCs, gas chromatographs, obviously monitoring all sorts of things in terms of gas constituents and calculating calorific value and all sorts. But they are gas analyzers. They're not set up for liquids. And so not only the analyzers don't like to see liquids, but the whole sampling system is arranged about not getting liquids into the system. So the guidelines from GPA, ASTM, API are that gas analysis should be sampled from the middle third of the pipeline diameter, particularly to avoid any liquids that might be there. So it is intended to be a gas phase gas phase measurement. And in fact, there's additional filtration between here and the analyzer to make sure that only gas reaches the analyzer as well. But consider the application for hydrocarbon dew point, then if we've got hydrocarbon that's already change phase, so heavy hydrocarbon if you like, and it's running in a stream down here, that's not going to be included in the measurements taken in the gas phase up here. So yeah, it can be quite a problem. So what we've found really when looking at results when lines are pigged, it's the TEG, the MEG, and the heavy hydrocarbons. These liquids are used in gas processing to dehydrate the gas, and it's when they're not separated properly that they carry forward into the gas line. And also heavy hydrocarbons carry forward as well. It may be lube oil or something like that. So what we have here, let me just move myself down here. What we have here is LineVu, and it's a camera system. It sits over the pipeline and hopefully attached to existing infrastructure. So, this is a standard tapping point that probably already exists on the pipeline. Standard isolation valve, and then we sit on top and we look through that valve into the pipeline below and monitor for any activity that shouldn't be there. So in theory, it's just gas moving at 25, 30 miles an hour. We shouldn't see any activity at all, but it's when some contamination is entrained in that gas that we start seeing activity, and we can use image processing to report that. So we're not asking operators to watch the video 24/7. They can if they want, but it gets really dull. And we use image processing, as I say, to trip that alarm and notify operators of what's going on. So when we start thinking about how this can be applied to the industry, you get some quite large numbers quite quickly. And we're going to look at the gas journey just in overview on this session. We go into gas treatment systems in a lot more detail in a separate session based on gas processing, and gas networks is a third session on gas networks and looking at where they see the benefits on this piece of kit as well. So we were trying to get our head around what was going on in a pipeline, really early stages in the project, really. And this is a 2-inch perspex pipe, really, and we're putting gas in that is round about the right velocity for what we want to see, and we're injecting oil, and you can see it immediately. It's thrown up to the ceiling of the pipeline, and then under gravity and a mixture of gravity actually and flow, it makes a full annular flow. So this is where the complete circumference of the pipeline is covered with a film of oil. And as we move further away from the injection point, then that process continues, and we eventually see a stream at the bottom. You can just about see that now. And apologies for the camera work in a minute. It gets a bit shaky, but what we're trying to show here is the beginning of a stratified flow. So you can see at the bottom, at the bottom there, you can see that it's running a lot quicker there than it is on the film up on the side of the pipe or at the top. And there we go. You can see that stratified flow quite well at that point. So yeah, and that's what we were expecting to see in a pipeline, and everybody knows about full annular flows and stratified flows, in mixed phase flows. That's quite common. What we weren't expecting is something completely different. So all the CFD models are based on what we're seeing here, and this is a 2-inch pipe. We are looking at 12, 24, 36, maybe in 52-inch pipes, and things happen very differently. There's no way you're going to get a full annular flow in a large diameter pipeline for a start, and there's no way you're going to get a clean liquid in a pipeline either. What we're seeing is actually a mixture of liquid, grease, metal particles, and it forms this gloop in the pipeline. Yeah, and this is the gloop. So this is what a pig should look like on the way in, and this is what it looks like on the way out once it's done a job. This is a smart pig actually to look at wall thickness. With all this muck on the walls, it's difficult for these things to operate properly. So very often the thing needs to be cleaned out before they can do any measurements. As you can see, we're seeing this gloop here. It's always black and gloopy, but sometimes it's black and gloopy meg, sometimes it's black and gloopy teg. But to a certain extent, it's got a lot of hydrocarbon in there as well. And the results of contamination are not easy to digest either. Hydrates is the scourge of the industry. We've got some work to do there, but we think we can detect hydrates should they at their initial forming stage. This was a pipeline rupture as a result of internal corrosion, and what's happening is the liquids entrained in the pipeline come across the river here and get buried underground, and then a little bit later on there's some hills up here, so it creates a low point where the liquids pool and gently corrode the system. And then if they accumulate to a point, they'll come through as a slug flow, and that's when compressors and power station, gas turbine power stations are written off as well. So what we have is this LineVu system. Let me move myself again. LineVu system where we've got this in the hazardous area, class 1, div 1. It's also ATEX zone 1, and then that's cable linked to the system in the safe area where we have the interface box and LineVu controller, which are normally side by side, but they can be separated if necessary. We've put up to 100 meters of cable. If we wanted to go further than that, we'd convert to fiber, and then we can go as long as we like, really. And then we can feed live video if necessary to the control room here. But what we have here is a cell phone transmitter, and we can get in and poll this for every 6 minutes. We do this to make sure the system's healthy, and we can also look at the video and make sure that's all what it should be as well. But this is also used to transmit text messages, emails to whoever is an authorized user and has requested that alarm to be sent to them. And we can attach short video stretches and still shots on that notification as well. There's also a mobile phone app, so on a tablet or a mobile phone, then a service engineer can get a live view of what's actually going on in the pipeline, which can be quite useful. So this is LineVu in more detail. This is the camera can, and it's split into two. There's a top chamber and a lower chamber. So this lower chamber is a secondary containment vessel. So if we did have a problem with a window or a back seal, then we're still safe. There's no loss of containment, and that gives us the safety level that we need to attach this system to a gas network, or in fact any gas system. The camera and illumination are sitting on the heatsink here, and that generates heat, which we use to gently heat the windows, so that even in condensing conditions within the pipeline, we're not going to see condensation on the windows. And this is the user interface. On this installation, we've got it on a 24-inch pipe. You can just see there's a flange adapter here. There's this little thing here. We can use that vent to either depressurize. If we're taking this off of the line, then we can close the valve and depressurize and then take that off safely. One of the questions we always get asked actually is how do we keep the optics clean? And of course, we're sitting above the pipeline here. This is a dead leg. This section, so it acts as quite a good cushion for us, and we've not seen contamination on any window so far. Having said that, it's a camera. You'd see it if it got contaminated, and you'd shut the valve, vent this off, take this off, clean it, and put it back on. It's not a big job. So this is the user interface, and you've got a measurement scale here to give users an idea of the size that they're looking at. Unfortunately, I can't share any video with you because it's client confidential, but this is a still shot. We always have flow moving from left to right, and this is some debris just sitting on the bottom of the pipeline. So imagine yourself standing on top of the pipeline looking down into it, and this is what you would see if you were there. Yeah, this section is chosen because this gave us our first detection. This flashed on for about a second or so, and that was our first detection of movement. So we can be quite sensitive, actually. This lot here is housekeeping data. This is the stuff we monitor for health, and it's overlaid on the video, so we can see everything that's going on. Time and date stamped, obviously. And then we can control the focus and the LEDs, the illumination, and the detection threshold. And we can do all that remotely. We can also reboot it remotely and do software updates remotely as well. So where's the benefit? Well, really, it's in gas treatment. You know, if on foaming situations, if we can get in and put a LineVu on the gas inlet and alert the operator that there's liquids there, then maybe we can do something about that. You know, foaming problem causes about a 20% reduction in productivity. That's figures from both the Middle East and the USA are putting it at that sort of level. So, you know, we just have a fraction of that, and you know, it's worthwhile doing. And then on the custody transfer points, well, you know, contamination events cause a permanent reduction in the pipeline diameter. You know, what we've seen is the sludge gets separated in the pipeline, so there's a separation process going on there, and we've seen the lighter ends being drawn off by the rapid gas flow above the sludge. So what remains is that solid matter, and that causes a permanent reduction in pipeline diameter. So flow meter stations, physical measurement, are a problem with if that process is going on. You know, as I say, it's a permanent reminder of the fact that there has been a contamination event, and it can make a considerable difference on physical measurements. To give you an example, just a 1/4 inch of debris can cost about $1 million a year on a 100 million scuffs per day flow. So it's quite significant. So there we have it. Let's say, any questions, any comments, feedback, by all means, send me an email and we'll start a discussion. And hopefully see you again soon on one of the other webinars we're doing on gas processing and on gas pipelines as well. So thanks very much. I'll stop sharing and say goodbye.